Okay, welcome back. Last time we developed the evolution equations for curvature and metric in a rather general setting for general speed functions. We had a family of mappings from a manifold into some Riemannian target manifold moving by speed f nu, and f was supposed to be a function depending on the principal curvatures of the hypersurface, and nu was the exterior normal. And then for this evolution equation, we had established general evolution equations for the metric, the second fundamental form, the normal, and so on. Today, I would like to look at the special case where f is the mean curvature. So, mean curvature flow would be the case where f is equal to h, which is the sum of the principal curvatures. And then in this case, we get the evolution equations by just inserting the speed in our formula from the previous setting. We get a theorem that, first of all, the time derivative of the induced metric on the hypersurface is equal to minus 2 times mean curvature times the second fundamental form. This implies that ddt of the inverse metric, upper indices, is equal to plus times second fundamental form times h, and then ddt of the volume element on the surface is minus h squared d mu, so it's pointwise decreasing. And then in the second step, you get the ddt of the unit normal is just the tangential gradient of the mean curvature. And finally, you get that ddt of the second fundamental form is just the Hessian of the mean curvature. Now I have to be careful with the sign, and then you get minus h times the square of the second fundamental form, and minus the ambient Riemann tensor in normal direction, I normal direction j. And this is often more useful if you write this in terms of the Weingarten map. So let me add this. If you raise one index, you get ddt of the Weingarten map is gradient I, gradient jh. And then from raising the index, you get plus these two terms, such that overall you end up with plus h times the square of the second the square of the Weingarten map plus the Riemann tensor of the ambient manifold. Now, this is the system of evolution equations that governs everything, but it's not so useful yet because, well, you don't see the parabolic nature so nicely here in this set of equations. In particular, this term here, second derivatives of the trace, you would rather have the trace of the second derivatives of this tensor. So you like to flip this. You see already the parabolic nature. If you take the trace of this, you get that ddt of h is Jacobi operator of h as it should be. switching in normal direction to the hypersurface. So here, to have this in the parabolic form that we want, one needs to use the commutator identities for the second derivatives of the second fundamental form. Now you can write down the commutator identities in the most general form. You can say what is the difference between di, dj, hkl and dh, dk, dl of hij. Here in this case, since we're dealing with Laplacian, we just need the commutator identity for the Laplace within. So this is known as Simon's identity due to James Simons. And I just stated in Rn plus 1 because otherwise you get lots of terms that involve curvature and even gradient of curvature in the ambient manifold. So in the Euclidean space, this just says that the Laplacian of the second fundamental form is equal to the Hessian of the mean curvature plus h times the square of the second fundamental form minus a squared, the second fundamental form, where a squared is just the sum of the squares of the principal curvatures. It's the squared norm of this tensor. So another way of writing this would be h upper ij, h lower ij, sum over I and j. Now, if you use this commutator identity, then the evolution equations that you get here, for example, writing 4, this is equivalent to the equation ddt of hij, one index up, one index down, is equal to, and then this becomes here the Laplacian of hij, and then these terms combine perfectly, so this becomes here plus a squared times hij, and in the Euclidean setting there is no such curvature terms. So this would be the evolution equation for the curvature in the Euclidean setting. And the important thing here to notice on this system is that it's first of all nonlinear. It has this cubic term here on the right-hand side. And it has here a Laplacian, which of course depends on the induced metric at times t. So it's called a reaction diffusion system. So this is the reaction part. Terminology comes from chemistry, of course, where you have many components that react with each other and which are diffusing at the same time in space. And here, so here you have the diffusion part. Now, the special thing about this geometric evolution equation is, of course, that these two things scale the same way. Two derivatives scale the same way as a square of the second fundamental form. And the other thing is, so it's sort of geometrically right. So 1 over time also scales like square of second fundamental form. So everything scales in the same way. But then here, the important thing is that that this operator here is really diagonal. So the second derivatives hit exactly the same component that you compute the time derivative of. That makes it special. And for each component, the speed of the diffusion is the same because this operator is invariant under the orthogonal group. So because you have sort of this isotropy in terms of the diffusion, this reaction diffusion system allows the application of the maximum principle in a way that would not be possible for more general reaction diffusion systems. So it's a very special thing in this sense. And let me just make the remark that this is a similar structure to the reaction diffusion equation for the Riemann tensor and the Ricci flow. So in the Ricci flow case, you had a abstract Riemannian metric that was moving in direction of minus twice the Ricci curvature of this same metric, and then doing a similar long calculation that, like we did to derive the evolution equation for the hypersurface curvature, one can arrive at a evolution equation for the Riemann tensor of this evolving metric. And it turns out you can show that this is the Laplacian with respect to the evolving metric of the Riemann tensor plus some term which is quadratic in the Riemann tensor. So you have a reaction term here in the Ricci flow, and you have a diffusion term. And while this is quadratic and this is cubic, it still fits perfectly together because of the different scaling. Riemann tensor scales like the square of the second fundamental form. So this is in fact the same scaling as in this equation. And you have the same structure here of something that has same speed of diffusion in all directions and is hitting exactly the same component of the Riemann tensor that you take the time derivative of. So this term here is exactly the same as here. The only difference is that this quadratic term here has other algebraic properties than this second fundamental form cubic term here. So the difference in terms of a reaction diffusion equation between Ricci flow and mean curvature flow just lies in the reaction terms. Now, there are some easy consequences that one can get immediately from the reaction diffusion system for the second fundamental form, looking at mean curvature flow. And then you can get estimates from the maximum principle. So the parabolic maximum principle. First of all, let's just look at the simplest thing one can do, and then we look at some scalar quantities. For example, when we look at the equation ddt of the mean curvature, we just have this equation. And this immediately implies, because h is a factor here, that on a compact smooth manifold, if the mean curvature has a sign, it will always maintain that same sign under the flow. So proposition, if the ambient manifold is smooth and MNT is also smooth, then positive mean curvature is preserved. In fact, non-negative mean curvature is preserved under mean curvature flow, just by the parabolic maximum principle, completely independently what the Ricci curvature in the ambient manifold is. Now, if the Ricci curvature is non-negative, then of course, if you start with strictly positive mean curvature, this will tell you that you get a singularity in finite time. So this is proposition 1, but the second part, if the Ricci curvature in the ambient manifold is greater than 0, then you just get from here that ddt of h is greater or equal than Laplacian of h plus, and here a squared is the square of the second fundamental form. The square of a matrix is always bigger than 1 over n times the trace squared. So we get that this is bigger than 1 over n times h cubed. So from this you get an actual estimate if the mean curvature happens to be strictly positive at time 0. Right? So if the mean curvature is bigger than some h0, strictly bigger than 0, then it follows that it must be true that the minimum of h over the surface at time t is bigger than some constant c1 divided by 1 minus the constant c2 times t for all t between 0 and 1 over c2. In particular, and here there's a square root, has to be scaled the right way, right? 1 over this, in particular, the maximal time of existence of a smooth solution maximum time of existence of a smooth solution is less than 1 over C2. And you can determine C1 and C2 from H0 by solving ODE ddt of phi equals 1 on n times phi cubed. Well, it also depends on n, of course, right? So it will be something like, this time will be something like 1 over h0 squared times some constant depending on n. So that this is an exercise. So you can actually use already for scalar quantities the maximum principle and get statements about possible behavior of solutions from a simple curvature condition on the ambient manifold and on the initial data. And of course, this estimate is going to be sharp on a cone, or in particular in Euclidean space, if you start with a sphere. So this is sharp. This estimate is sharp on Sn, R0 sitting in Rn plus 1, because then the mean curvature will exactly solve this ODE, because it's just one radius determining the mean curvature at each time. Okay. Now, there's more interesting scalar quantities one can look at more nonlinear ones than the mean curvature. So other scalar quantities say Q, depending on the principal curvatures, satisfy a parabolic PDE again. Namely, you can write ddt of Q is equal to dq with respect to the second fundamental form, right? You use the chain rule, and then you get ddt of Hij, and you insert this, so you get dq dHij times the Laplacian Hij, and let's do this again in Euclidean space. Just in this is Rn plus 1. And then here's an important principle. So you start to compute such an evolution equation, and you know that on the other side you want to have the Laplacian, because it's a natural operator acting on the right-hand side, like in the case of the evolution equation for the mean curvature. So it's always a good idea then to just compute the Laplacian of this quantity. So the Laplacian of Q is, of course, gradient L of the derivative of Q with respect to L, which is dq dHij by the chain rule again, times gradient L Hij. And this gives the term we already know, dq dHij times the Laplacian of Hij. And the extra term comes from the derivative of Q, so we get a second derivatives of Q with respect to the second fundamental form, multiplied with gradient L Hmn times gradient L Hij. And this lets us write the evolution equation for any scalar quantity Q like Laplacian Q on the right-hand side, and then adjust it for this term minus the Hessian of Q with respect to the second fundamental form. And then this term here, if the quantity Q happens to be homogeneous, then here you get the quantity Q back again with multiply with the degree of the homogeneity. So you get plus the degree of Q multiplied by Q times A squared on the right-hand side, if Q is homogeneous of degree Q. Okay. And this is now again a parabolic equation which has a first order term, of course. And then an interesting question is, under what conditions can you say something about this term? Well, obviously you can say something if this term Q here is concave, because then this is a non-negative term, and you can argue with the maximum principle like we just did before. So in particular, if Q is concave as a function of the lambda i's, then the second term on the right-hand side is greater or equal to 0, and you can get several results from the maximum principle as before. And I don't carry that out, but you can get similar results as we just proved for the mean curvature for such quantities Q. Are there such interesting quantities? Yes. Particularly useful quantities in this case would be, for example, quotients of elementary symmetric polynomials of the lambda I. So, example. So if we set Sk of lambda to be the sum over I1 less than I2 up to Ik of lambda I1 times lambda I2 all the way up to lambda Ik. So the sum over all these terms of order k, then we get the homogeneous symmetric function, and it's not well known that the following is true. First of all, it is true that Sk to the 1 over k is concave, where Sk is positive. And then the second interesting thing is that the quotient Sk plus 1 over Sk is concave on the set where Sk is positive. It's an interesting fact. You don't only need the denominator to be positive. You don't need the numerator to be positive for that. So this is important in some applications. So there's plenty of examples of concave functions that one can apply the concavity and apply the maximum principle on these quantities. So you get, in particular, that lower bounds, positive lower bounds on these quantities are preserved by a mean curvature flow in Euclidean space. So in particular, the meta theorem is lower bounds on such quantities under mean curvature flow can be obtained by the maximum principle. Of course, once you get it by the maximum principle, you may also get some interesting integral estimates for some other applications. Just drawing your attention that these are interesting quantities and they interact nicely with mean curvature flow in the way I just explained. Now, the next thing I want to show you is that there's a nice natural criterion how long a solution of mean curvature flow exists and when we have to expect the singularity. How can we distinguish whether the flow develops a singularity, something goes wrong, time interval of smooth existence ends? How can we predict this a priori? We have got some results like that, but how can we also along the flow determine whether the flow can be extended a little bit further? And it turns out that because of the parabolic nature of the flow, all we have to do is bound the curvature of the surface. As long as we can bound the curvature, the surface can always be extended a little bit further into the future. So in order to control the flow, all we need is the curvature. Means it cannot happen that, say, 27 derivatives of the metric and the position vector remain nice and smooth, and the 28th derivative blows up. This kind of behavior cannot happen because of the parabolic nature. And to demonstrate this, we will have to look a little bit at what happens to the higher derivatives of the second fundamental form. But first, let's formulate the result theorem. If and I formulate it in the Riemannian manifold, but I only give you the proof in the Euclidean setting. So if the initial surface contained in Nn plus 1 G bar, and this is assumed to be smooth, again, is compact without boundary in a smooth Riemannian manifold, then the curvature flow has a solution on some time interval zero less than time interval 0t, where capital T, yes, and let's call this T max. T max is certainly positive. This is our short-time existence result that I mentioned in my last lecture. Now, it may be a solution that exists for all time, but it's a smooth solution on this time interval. But if the time interval is not infinite, if it's finite, if T max is less infinity, then the sup of the second fundamental form over the surface Nt is unbounded as T is to T max. In other words, the only way the flow ceases to remain smooth in a finite time is at the end of the time interval, the curvature tends to infinity. So this is the result. Let me make a remark straight away. So this can be weakened. This can be strengthened in the sense that the criterion can be weakened, can be improved. It turns out to be enough that MNT remains a graph of bounded slope locally over some tangent plane or over some reference surface, some smooth reference surface of a uniform size. In other words, if you can write it, as long as you can write the surface locally in a time interval in space of fixed size as a graph of some function of gradient uniformly bounded, then this gradient bound on the surface, rather than the C2 bound implied by the bound on the second fundamental form, is enough to give you smoothness for all higher derivatives and lets you extend the solution a little bit further. In other words, the theorem formulated here says if the surface sort of locally is like a nice C2 surface in a uniform way, then we can extend the solution. This result can actually be improved to a statement, which of course has to be formulated more carefully than I did it here, a statement saying that if you can locally control it as a surface in C1, then you can already extend the surface somewhat further. Maybe we come back to this later in the course. I just want you to know that this is, it's interesting as it stands, but it can be improved in this way. Now, to prove this, we want to show proof. So I give you a sketch. I want to show that the assumption that the curvature is bounded implies that all higher derivatives of the curvature are bounded as well. For that, we need the evolution equations for the second fundamental form. Or the derivatives of the second fundamental form. Okay. So the claim is proposition. First of all, we get that ddt of any derivative of the second fundamental form can be expressed as the Laplacian of that derivative. Think of it component-wise, plus a reaction term, which may involve all the former lower derivatives in a certain way. And what you get is a linear combination of cubic terms, just like in the evolution equation of the second fundamental form itself, but now the cubic term will have various derivatives. Now from scaling, it's completely clear how many derivatives there can be in total. So we just have to allow them to distribute in a certain way between these cubic terms. So let's write this in this way, that we have terms here with derivatives I, j, and k such that the sum of these derivatives is exactly m. And then we have terms that multiply an i's derivative with some j's derivative and some k's derivative. And the star simply means that there can be arbitrary linear combinations where the coefficients just depend on n, and there can be traces involving the metric g. So the star here means that we have linear combinations coefficients depending only on n, and maybe there are traces depending from Grj. But not first derivatives of Grj. Okay. Right, so this is the structure of the evolution equation of the gradient, and now this implies that we get an upper bound on the time derivative of the length of any of these derivatives, and we can estimate this by the Laplacian of the same quantity, and then because this is Laplacian of a square, we get a good term involving the next higher derivative squared, and then we get a term where we have again something like this. So we get I plus j plus k equals m, and then here there is a constant depending on n and m times, and here, because we have a square here, we always get one factor, which is the derivative of order m, and then we get other factors coming from the i's derivatives, the j's derivative, and the k's derivative. Okay? So we have this kind of estimate. Now for the proof of this, you prove this by induction on m. First of all, it is clear that 2 follows from 1, since the Laplacian of the square is equal to twice the Laplacian of gradient ma times gradient ma plus twice gradient m plus a r squared, right? Because when you do gradient k, you get 2 gradient ma times this, and then you get the term where you get the Laplacian, you get the term where the gradient k from here falls 1 on here and 1 on there, and that's exactly this term. And the other thing is, of course, that if you here that in the square, the square is taken with respect to the metric. So when you take the derivative of the metric term, you get this guy squared multiplied by the derivative of the metric. But the derivative of the metric is like curvature squared. So you get one of these terms where j and k are 0, that's the curvature squared, and where the I is equal to n. So you get this term which is exactly like this one times the curvature squared. Okay? Right, so this follows from that, and to compute 1, you need, because it's covariant derivative, the key thing you have to do is compute what the derivative of a Christoffel symbol is. So to prove 1, note that ddt of a Christoffel symbol, so this is ddt of 1/2 the IL, and then here we have the derivatives of the metric. Okay, GLJ minus the XL GK. Okay. So this is obviously now this trick again, when you take the time derivative, you can pick a coordinate system which is a normal coordinate system, then we don't have to differentiate this. Just differentiate that. So this leads to something like from the evolution equation of the metric, this leads to something like minus gradient I of HLK minus gradient I of gradient, what am I saying, gradient K, sorry, gradient K of gradient K of I J, and then here plus gradient L of H I, and L, this is gradient I, making a mess of this, huh? This is there's too many. This should be a J here, and then this is gradient J, and this is gradient HIK, like this. Now we got it right. Gradient KIJ, and this is gradient I HJK. Second. Now in our notation, this can be written as A star gradient A. Okay? Because this is one curvature term times the derivative of curvature. So in this notation where we don't care what the terms actually are, but what the structure is, we get this equation. And then, of course, the other thing you need to know is that if you swap a derivative right, so this is when you do the ddt, and then you end up that you end up with something like gradient m of Laplace A, and on the other hand, you want Laplacian of gradient MA, right? You want this commutator comes up, because when you do ddt, you have this term coming up, but on the right-hand side, you want the Laplacian of gradient MA. So you need to know you have to switch the two, so you have to compute what this commutator is, and commuting sort of these derivatives through, this leads exactly to the kind of terms that I mentioned. So this leads exactly to terms which can be written as let's see. Right, so these are exactly the terms that are up there. So you can write them as I plus J plus K equals M of gradient IA star gradient JA star gradient K. And so you convince yourself that this is what happens when you commute second derivatives, and then you use the evolution equation of A. So so the third ingredient you need, of course, is that the ddt of A itself is equal to Laplace A plus A star A. So this is your starting point, and then you do it by induction. These are the three ingredients, and then you do it by induction by N. I think to convince yourself, it's enough if you do it for the gradient of A and maybe the second derivatives of A, and see that this is that this pattern works to give you these estimates. One. Now, once we have this estimate here, it's clear that a bound on the curvature implies a bound first on the first derivative, then on the second derivative, and so on. Let me just show you the first two steps. So assume now that the sup of A squared on the surface Mn cross 0t is less than sum C0 squared less than infinity. Assume it is bounded on the whole time interval. Then bound in the first step gradient A. Well, we have ddt of gradient A squared is less than Laplacian of gradient A squared, and then we have the sum of terms, and in this case m is equal to 1, so we get one term gradient A, and then there must be one of the others must be gradient A, and the others must be just curvature. So we get plus a constant depending just on the dimension times gradient A squared times A squared. It's the only term we get. But this can be estimated by a Laplacian of gradient A squared plus Cn times C0 squared times gradient A squared. And now the point is that this term here, because the nonlinear term here that usually causes the blow-up is bounded by assumption. This is just linear in gradient A squared, which means that this term by the maximum principle can only grow exponentially. That's the philosophy. So we take for example, now a quantity, if you see this formally, you see that G, if you take gradient A squared times e to the minus Cn times C0 squared times t, where these are the same constants like here, we get that ddt of G is less than Laplacian of G, because this does not contribute to the Laplacian, it's just a factor independent of space. And then we get from here exactly the negative term that we have a positive term there. So we get this and nothing else. So this means that G, by the maximum principle, that G, the sup of G on Mn cross 0t is bounded by the sup of G0. But at 0, this is 1, so we get that gradient A squared, the sup of gradient A squared on MNT is less than the sup of gradient A squared on the initial surface times e to the Cn times C0 squared times capital T. And capital T was assumed to be bounded. So this is less than some constant C1 on N C0, and T max times the norm of gradient A on the initial surface. Okay. Now, this would be sort of the very dirty, quick, dirty proof that we get a gradient A squared bound. Now, similarly, in the second derivative, you now write down ddt of the second derivatives, and then you use the fact that you have already bounded the first derivatives, and the curvature is bounded by assumption, and then you see you get a similar inequality. So iteration works easily. Now that you don't have to do it that dirty. First of all, turns out you want to get rid of the estimate depending on the time. So remarks. First remark is the estimate can be made independent of capital T. And this uses the fact that if you take the ddt of the second fundamental form squared, I'm talking just Euclidean space at the moment, then it's turns out to be Laplacian A squared minus 2 gradient A squared plus 2A to the 4. One. Equation for the second fundamental form. So we could have used this good term. Also, rather than taking this exponential, we could have added enough of this equation to that equation to kill this bad term. So we could have used G tilde, which is gradient A squared, rather than multiplying with this time-dependent function. You could just add a huge amount of A squared, where the number n is, for example, exactly this bad term, Cn times C0 squared. And then you get that ddt of G tilde is less than Laplacian of G tilde. And in this case, from the here, you get minus 2n, and one of them is killing this term. The other one remains. You still have a minus gradient A squared left over. And you pay for that with this term here. But A to the 4 is estimated by C0 to the 4, which is a constant. So this tells you, because you have now this term on this G tilde here on the left-hand side, you can write this as Laplacian of G tilde minus n times G tilde. And then you get, you made an error, which is like n squared times A squared. And n squared plus 2n C0 to the 4. But this tells you that G tilde by the maximum principle again cannot get a new maximum which is larger than this number divided by n. So this is, so G tilde cannot have a new maximum larger than n C0 squared. This is C0 squared plus 2 C0 to the 4, which is something like, and this was again C0 squared, which is 2 plus Cn times C0 to the 4. Therefore, G tilde must be bounded either by the initial data or by this quantity. And this is then independent on on time. So G tilde, so this means gradient A squared is less than the maximum, then the sup of gradient A squared on the initial surface, or 2 plus C0, 2 plus Cn times C0 to the 4. So we've managed to get now an estimate which is independent of time. And you can also do this for all the higher derivatives. The second remark I want to make is that this estimate is still dependent on the initial data. Turns out you can even make the estimate independent of the initial data by squeezing a t in there. So you can even make the estimate independent of the initial data. Namely, you can take take this trick that we just used, use a function like g hat to be, take something like t times gradient a squared plus some number m. Now m is not a good idea. L times a squared. And when you do then g, the derivative of g hat, you get again that this is less than the Laplacian of g hat. And then from here you get minus 2t gradient second derivatives, which we throw away. From here you get minus 2L gradient A squared. Then you get the bed term 2L A to the 4, which is C0 to the 4, coming from the evolution of this. And then you get one extra term coming from the time derivative of this guy. So this is one term like gradient A squared. But now we know how to absorb this term in here. So we can use exactly the same argument, and we end up with the fact that this thing is bounded by its initial data. But then this thing being bounded by its initial data plus some constant only involves the C0 squared. So from this you get that gradient, the sup over m and t, gradient A squared is less than the constant depending on n times C0 squared divided by t. And this is, of course, an estimate which is not so good for small times. So our other estimate is valuable if you know that initially the gradient of the second fundamental form is bounded, then you get a better estimate for short times. But this gives you an estimate for later times, which is completely independent of the initial data. It only uses the fact that the initial data had bounded curvature. Yeah? So it's estimate, we call this an interior in time estimate. And in particular, it means if you wait a little bit, you get the derivatives bounded. And you can work this out. There's all, you get something like sup of the nth derivative of a over mn t. This is a good exercise. Then the constant, depending on n and m, times c0 squared divided by t to the n. So, and this is a scaling invariant estimate. It survives sort of with the same constant if you multiply everything with some constant lambda and then replace here the C0 by C0 divided by lambda and multiply the time with the, stretch the time with the appropriate term lambda squared, and then it will actually fit together perfectly. And you get the same estimate in the rescaled coordinates and rescaled time. Okay, so one can improve this greatly, and one could even make this also an interior estimate in space by using some cutoff functions. I don't need this at this stage, so I don't do it because we just want to prove that one theorem. But I wanted to show you that by using more and more clever test functions, one can get better and more precise estimates. How the parabolic nature of the equation improves, smooths out the solution, at least for short time. So this is for some, of course, only true for a time interval. If t is in a time interval which goes up to some constant depending on n times c0 to the -2. If the time interval is longer than that, of course, this will no longer be true. And I leave the details to you. Okay. So the upshot is, if you now do this by iteration on n, you get a bound. So proof of theorem continued. We now have that the derivative m squared is less than a constant, large constant, depending on n, m, and if you like, the sup of the curvature on the initial, let me just write the initial data. On mn cross 0 T and of course, depending on our assumption, C naught. And we have this for all n. Okay, so we get this bound. So now we would like to show that as we approach T max, we get a nice limit metric on which, in the limit surface on which we can extend the flow. Now, the speed of the surface is given by the mean curvature. So by assumption, ddt of the position vector, this is just the mean curvature vector, the length is bounded by, let's say, n times C0 is less than infinity. So this immediately means that f of xt is a Cauchy sequence as t tends to capital T max for all x in Mn. So we definitely get a limit point in the ambient manifold as we approach the final time interval. The question is whether this limiting function is again a parameterization of a nice surface. So for that, we need to understand the first derivative, which is the first fundamental form, the induced metric on the surface. So we need to control that the induced metric remains a proper induced metric. And that, of course, implies that the that f remains a nice parameterization. So show that Dij of x and t is equal to the inner product of the tangent vectors remains non-degenerate. And this is a little lemma that was actually used by Richard Hamilton in Ritchie flow. But I'm sure it's been known to other people as well. So if Gij T is a family of positive definite metrics, and the integral from 0 to t of ddt Dij measured with respect to g of t dt is bounded by some constant c1 less than infinity, then all Gij of t are uniformly equivalent, and Gij of t converges to some Gij of capital T positive, which is again uniformly equivalent to the initial metric. And the proof is quite simple. You take any tangent vector take any vector x same, yeah, independent of time, just a vector, and then compute how the logarithm of the length of x with respect to gt changes with respect to time. Okay. Now, by the fundamental theorem of calculus, we can write this as an integral from 0, well, say from s to t of ddt or dd tau of gij of tau at this tangent space times xi, xj, they are not dependent on tau, times d tau. And if we want to estimate the difference between them, we can estimate this by the length of that. And this is, of course, now exactly, and I forgot here ddt because I'm taking the logarithm. I'm getting an x squared in the denominator times. Okay. So if I now apply Schwarz inequality, I get exactly this integral. So this term here is exactly less than C1, less than infinity, by assumption, because Schwarz inequality, this term cancels against the x tau to the -2, and I'm exactly left with this integral from s to t, and I estimate this by the whole interval, and this is bounded. But this logarithm is nothing. The difference of the logarithms is, of course, the logarithm of the quotient. And so I get the logarithm of the quotient estimated both away from -infinity and from +infinity. So this tells me that the x squared at time t divided by x squared at time s is bounded below by e to the -c1 and bounded above by e to the plus c1 times no, nothing, has nothing to do with t, e to the plus c1, so fixed constants. And this means, of course, this is equivalent to saying that the metric at, and then I can, of course, choose s equals 0, the initial time, and then I see that all the lengths are uniformly equivalent. So as in terms of matrices, Gi, A, Ij of t, as matrix is less than E C1 times Gij of S, in terms of eigenvalues of matrices, and minus C1 Gij of S. And in particular, I can take S equals 0 and see that they are all uniformly equivalent. Now, concerning the convergence, in the next step, you see that because of this, that the Gij of xx, then Gij T xi xj converges to Gij of capital T xi xj for all x Tmn, and Gij of T satisfies star. In other words, you get that the Gij is a quadratic form, converges because of this estimate. But if it converges as a quadratic form, then by polarization, it also converges as a bilinear form. So just use polarization. And you get that Gij of T of xi yj converges to Gij of capital T xi yj for all x, y in T. Okay, and this is proving this little lemma. So the parametrizations converge, and also their first derivatives converge uniformly if we have this uniform bound on the derivative of the metric. And this, of course, recall, was given by the square of the curvature, and this curvature was assumed to be bounded. So our assumption is satisfied, and therefore the parametrization and its first derivatives converge. But now you can use the estimates on the higher derivatives to see that all norms are bounded, and then in the next step. So we just got, so f of t converges, at the moment we have converges in C1, and then higher derivative estimates on A show that the Christoffel symbols converge, and the second fundamental form and all the derivatives. First by Arzela Ascoli converge. Ascoli, but then once you have the second derivatives converge, you also get that the equation converges. And you get the ddt of f equals mean curvature vector on the whole interval, on the closed interval, all the way up to the end of the interval. And so you get surface Mn capital T smooth. And now you just use the short time in existence result to see that you get a smooth solution of this equation on a short time interval. Get smooth solution of curvature flow on the interval T max to T max plus epsilon, for some epsilon positive by the short time existence, which I mentioned to you last time, and of which I gave a more precise proof in the other course on Ricci flow, and you can find that lecture online. So there is the short times existence result, which we now use to get solution on this short time interval starting at T max. But now this solution has to fit together with the previous solution because the mean curvature vector fits together at T max, because we get a smooth solution starting from T max, and we have a smooth solution ending in T max, where the mean curvature vector agrees with the speed. So our equation now solves. So to get a solution which is smooth, C2 would be enough, and then it's smooth, as we know, smooth on all the way from 0 to T max plus epsilon. But this means this is a contradiction, because we assumed that this was the maximum time interval where you have a smooth solution, T max. But now we, under the assumption that the curvature is bounded, we were able to extend the solution. So it was not the maximum. This is a contradiction. The only resolution is that the curvature cannot have been bounded on this whole interval all the way up to T max. Proofs. Okay, so this concludes the proof of this result, and it's also giving you a criterion how to single out singularities. Singularities occur when the curvature blows up, and I mentioned that this can be weakened, and I also mentioned that you get nicer a priori estimates depending not even on the initial data. So we could have strengthened this with these other remarks. We could mention this, strengthen this theorem in the following way. So we could also say theorem, if the initial hypersurface in n plus 1, T bar, is of class C2 with bounded curvature sup a squared on the initial surface less than C0 squared, then, and again assume compact, no boundary, then there exists a unique solution of mean curvature flow on an interval 0, 0 up to T max, where T max is at least a little constant depending on n times C0 to the minus 2. This follows from the estimate that was interior in time. You get an estimate at least on the higher derivatives, at least to this time there. And if T max is finite, then a squared is unbounded as T approaches T max. Okay. So we have strengthened the result in the sense that if we just have a C2 initial surface and we have a bound on the curvature on the initial surface, then we get a lower bound on the short time, on the existence, because we have this estimate interior in time up to some time which is like 1 on C0 squared. And we still have, of course, the result that the curvature then can only blow up if the curvature becomes unbounded. This can be proved by approximation, right? So you could take this initial surface approximated by smooth surfaces, and then on these smooth surfaces, you have the nice bound on the higher derivatives at all positive time, depending only on this initial curvature. So as you approximate, these estimates survive, and you end up with a solution that satisfies this lower bound on the time of existence. It's sometimes useful to have such a lower bound on the time of existence of your surface. Okay, that's enough for today. Thank you very much.